All right, so let me just give you first my 2 cents on the exascale perspective. About all these technicalities, don't worry. I mean, we and most of us in this audience will figure it out. It works the same way as Moore's law. We have a couple of years to see the perspective, and we adapt. And on stretching the imagination to figure out what are we going to do with all these resources. Well, come on, we're talking about improving resolution with a factor of 6. No problem. That's exactly what we need. So first, let's look at what we can do today. We are just at the point where we can converge on the initial mass function. We can figure out what resolution do we need to resolve the distribution of stars. So you're worried about the mass spectrum, we're worried about the mass spectrum. That's one of the main properties we want to reproduce. And today, if we normalize on known properties, and when we look at giant molecular clouds, that's the best scale because that scale is very well studied. So the figure on the left is from Larsson's 1981 paper. This has been known for 30 years. And normalizing to that, we can then check dependence on the IMF on resolution. We've done a parameter study, and we come up with affordability if we have a root grid of 2 physicists cubed and 9 levels of refinement, we essentially recover the IMF. We can then go to the next tuning point and say, what if we are satisfied with resolving it down to just a few solar masses because we want to have the exploding massive stars right, but we don't care to pay so much that we pay for the turnover and so on. Well, we can figure that out, and this is what we've done in this galactic fountain simulation that I'm not going to discuss more. Rather, I'm going to give an overview of work going in the other direction, towards smaller scales. So these are first of a kind ab initio simulations of formation of circumstellar disks. And the paper appeared on Astrophysics today, actually. I had a number for you here, but PowerPoint crashed on me, so I lost that update. But you can find it easily, of course, searching today's Astrophysics. What's new here is that we're zooming over a factor of 1 billion. We're zooming over 30 powers of 2. So when I show you animation, we're using about 2 orders of magnitude in the picture, of course. So I'm showing animations that zoom over 7 orders of magnitude. So far, this is a proof of concept. We looked at one solar mass star, the formation of one solar mass star. But the idea is to look at a statistically significant sample of solar mass star formation, because we suspect, of course, that the variation from star to star is significant, probably more significant than the uncertainty in initial conditions at the scale we are looking. So the basic idea is to anchor the dynamics in the well-known observed spectral range, the spatial range of giant molecular clouds. And the advantage of that is huge. It avoids having to pose unknown, arbitrary initial and boundary conditions if you want to study the formation of protoplanetary disks. And it's very similar to the idea of studying galaxy formation by starting out from the well-known fluctuation amplitude and the fluctuation spectrum on cosmological scales. The drawback is that you must cover about 9 orders of magnitude in size, from GMC scales to resolving the vertical structure of disks. It's not so much you have to go close to the star, but you have to resolve the vertical structure of a cold disk, okay? And the cold disk is very thin. So, however, it turns out that if you invest your AMR cells such that you have about the same number of cells in each level as you zoom into a star, it means that the cost scales linearly with the number of levels. So going to 9 orders of magnitude is only about twice as expensive as going to 4.5 orders of magnitude, which is the minimum you would have to have anyway. There's no sense in simulating a protoplanetary disk unless it's at least a few hundred AU big. And the vertical scale height is of the order of 0.01 AU. Okay? So that gives a 4.5 order of magnitude already. So why bother with inventing arbitrary initial conditions on this scale when you can do the whole problem?
Why does the time step not go down continuously with levels and thereby?
I have to postpone discussions because time is rather pressed. So let me explain. We do this in 3 simulation levels. And this partly answers your question. So the first level is a giant molecular cloud scale, where we refine with 16 levels, which gives a cell size of 120 AU. And that choice is so that we can afford a few GMC dynamical times. Okay? Then we go to 22 levels of refinement, which corresponds to a cell size of 2 AU. And that choice is based on being able to afford a few accretion times. Okay? So about 100,000 years for a solar mass star. And then we go to the deepest level, 30 levels of refinement, and that's chosen to marginally resolve the vertical structure. If you talk to people doing an MRI of disks, they need 16 or 32 points per scale height to do their thing. So this is really marginal. So this is a first-of-a-kind simulation where we tweak everything as much as we can, and therefore we have no problem thinking of getting a 6 times better resolution whatsoever.
I think the answer is that nothing reacts back up to
That's actually how the dynamics works, but it's not the way the dynamics works. All scales are present in the simulation, and AMR does local time stepping. So when we zoom into the smallest level, of course, everything freezes.
What I'm saying is you're not doing the refinement on the scale of 100-year time steps for 10 million years.
Of course not. No.
That's the answer.
But you see, I'm coming to all of that. It's a waste of time to discuss it because it's in one of the next view graphs, okay? It's going to be explained. So it's more rational to take the questions at the end. So this is a joke, but I think you take the point. So why not do the whole thing in unigrid? Well, it would take 100,000 ages of the universe because it requires so many operations. However, if you believe Moore's law, you can wait 80 years and it's going to be possible. You can perhaps doubt that Moore's law will continue, but that's actually the simple arithmetic, and it's amazing. So if you have something that you want to do and it's not affordable, well, you can try poking your brain and inventing a much smarter method, but you can also just wait and do something else in the meantime. So here's the answer to your question, okay? This is how we stack the simulations. First, we have a 10 million year simulation of GMC, which is supernova-driven, actually. We started off with a population of supernova that was artificially created, but later on, it's its own supernova that does the driving. We then select solar mass stars, and we have hundreds of stars forming to select from. So we select the ones that form out of cores between 1.5 and 2 solar masses because we expect mass loss in an outflow. So solar mass stars should start out with about 2 solar masses rather than 1. For this one star we have so far, we cover it with a much finer resolution and a much finer time step for 100,000 years, actually 200,000 years at the current time. And we then zoom in again in time. So each experiment here is just a few hundred years. But it looks at the beginning, at the middle, and at the end of the accretion history. And the accretion history is such that the early one is where the mass is only a few % of the final mass. It's a few thousand years after the birth of the zinc particle, and the accretion peaks after 5,000 years. So the first amazing result here is the structure of the disks. The first experiment, you can hardly see any disk. But if you look at the Keplerian velocity criterion, you find that the disk is, okay, I'll die without making so much noise. That there is a 1 AU disk at this point in time. So this sort of corroborates with the magnetic braking disaster that people have worried about recently. However, after 50,000 years at the middle evolution here, we have a fantastic situation with a collimated jet with about 100 kilometers per second outflow, wide wind, and a 10 AU disk, 10 AU Keplerian disk. And at the end of this, after about 100,000 years, we have a 100 AU disk with a very different magnetic field topology. Now the field is almost in the disk plane. And its strength I will come back to if you have questions about that. That will be answered too in the next few slides. So but first, here's an animation showing the whole zoom. And you should note that you get confused. So here we first zoom in into a particular filament and a core that happens to form a solar mass star. And that's this one. And we zoom in on that one. So now we're at the scale of about 50,000 AU and about 10,000 AU. And note that you get confused every time. You get new structures all the time, even though I keep the perspective. That's a significant thing. You zoom in with about a factor of 10 in density, and you lose everything. Here's the jet looking from top, and here's the thing from the side on a scale of a few AU. So we zoom out and we look at the structure here, and you see there's a nicely collimated magnetic field structure at the center and more centrifugal type structure further out. If we briefly looked at the structure in the late phase, this is a perspective on the disk from a size of about 15 AU, and zooming in, sorry. Back. Zooming in here, we find that if we look in the disk plane, it's not really a plane, but it has a mountain ridge in the back. Sorry about the resolution here. And the reason for that is that the magnetic field is not quite in the disk plane, but it's puffing up the disk at that particular location. So now we zoom out to look at the global structure of the magnetic field here. You see it's being pulled around, of course, by the Keplerian rotation, and so effectively that it's essentially in the disk plane very much. So let's look at the quantitative results here. The accretion rate peaks after only about 5,000 years, when the mass is still less than 10% of a solar mass. And it then decays essentially exponentially, reaching 10 to the minus 6 solar masses per year after 100,000 years. It peaks at 6 times 10 to the minus 5, which is a very reasonable accretion rate, if you ask observers. The most amazing thing here is the mass distribution with radius. The dashed line shows how it starts out in the very first part of the collapse. Very steep. But after only a brief time, it reaches the asymptotic slope shown by the full drawn line, which is the 3/2 line. That's exactly what you would expect from free fall. But this is not at all free fall. But it's something that scales as free fall, actually. And the reason for that can be understood if we look a bit at the dynamics. But first, another very important result, which is certainly obvious afterwards, but which people haven't really appreciated from back-of-the-envelope estimates. And it's even a point where observers are embarrassed to show their results at meetings because they think it's strange. The simple thing is you take the disk mass, which is a function of radius. There's no well-defined single scalar quantity called the disk mass. It's just a function of radius. You divide with the accretion rate, and you get a time. That's a replenishment time for that particular radius that you choose to look at. And the amazing result is that the time scale varies as a function of age, but it's of the order of years. Okay? So the disk is replenished and replenished and replenished many, many times during its lifetime. There's no way you can store things in it for a long, long time. And you might say, well, this probably depends on your lousy numerical resolution, and that will be answered then by Exascale. And I don't think we will turn out to be wrong at this. So at any one time, you can easily convince yourself that conservation of mass means that the spiral angle is essentially constant as a function of radius, and therefore the replenishment time is a constant factor times the orbit time. And in the beginning, it's a very small factor times the orbit time, and later on, it's a large factor times the orbit time. So this is a rather compact figure, and I'm sorry about that, but it's because the paper you can find on Astrophysics was a paper to the IO Symposium in Victoria, and it was limited to 4 pages, so the last figure had to be quite compact. So everything from the 3 models is in this one figure. First, the line type. The early model is dashed, the 50 kiloyear is dash dotted, and the 100 kiloyear is a full drawn line. Then the colors. Rotation is in blue, and because I wanted to show the magnetic energy in comparison to the rotation energy, I turned that into Alfvén speed. So the green is Alfvén speed. And the orange is velocity dispersion remaining when you subtract the orbital motion. And this is quite amazing. It's showing that, first of all, if you look at the Keplerian speed, initially you have only a 1 AU extent, but you do have a 1 AU extent of Keplerian scaling, which is shown by the dashed line up here. In the intermediate time, you have about 10 AU of Keplerian scaling, and late you have 100 AU, which is what I already said. The amazing thing is to look at the Alfvén speed. Early on, here's what it comes up to, and it scales the same way as the Kepler speed, okay? While nevertheless, the kinetic velocity dispersion is much, much lower. So this means that as the thing collapses and is not in Keplerian rotation, there is a balance between the work done by the gravity as it pulls mass in and the magnetic energy density. The scale is over 4 orders of magnitude with a Keplerian type scaling. And you can recover that at even the late time and the intermediate time. It's exactly the same behavior. That's quite amazing. It's not shortly, it's there today. So what can we pull out of this? Well, we can pull out the enormous importance of the magnetic fields, because they are the conduit that makes accretion possible, first of all. But it also makes outflow possible. And when I compare the final mass of the star in the initial 16-level simulation, it was 1.6 solar masses. In the 22-level simulation, it was 1.05 solar masses. So an outflow that emitted 1/3 of the mass was recovered by going to 22 levels. And exactly what it will converge to, I don't know. But people deduce empirically that about 50% of the mass should be lost in outflows when you form a star. So these two properties are intimately related. You can only lose angular momentum by having a magnetic field. And you can only lose it by ejecting mass, because that carries the angular momentum together with the pointing flux. A third speculative but very interesting possibility is that in the late phase, when you have still a strong magnetic field, that could suppress the turbulence that 30 years ago or more killed the Coleridge and Ward suggestion for how you create planetesimals. They simply said if you have dust in a disk, it will settle to a very thin disk because of dust particles are heavy. So you get a thin disk, and therefore you get instabilities. And you would form very quickly bodies of size, typically size of 10 to 100 kilometers, just as you want for planetesimals. But just a few years later, somebody killed the idea by pointing out, well, you will have a shear velocity between the disk and the remaining gas, and that will create turbulence by Kelvin-Helmholtz instabilities, and you wouldn't get a thin disk. So ever since then, people have rejected or not thought about the Goldreich Award instability. But maybe we can resurrect it as a very efficient way of forming asteroids, planetesimals.
Would it work in the presence of a strong magnetic field?
Who's asking something?
Would it work in the presence of the strong magnetic field?
In the presence of a strong magnetic field, you suppress the Kelvin-Helmholtz instability, because it prevents motions up and down.
But I mean the planetesimal accumulation of the Goldreich Award.
The dust is not influenced by magnetic fields. All you have to do is to suppress the gas turbulence, and then the dust would do its thing, as originally anticipated. So it's also encouraging that you can get a realistic outflow without resolving anything near the star. This is entirely driven by the disk, the Keplerian disk. It creates even this highly collimated jet with outflow speeds of the order of 100 km per second, as observed. And the outflow speed, as we know, is just similar to the Keplerian speed at the base of the jet driving. So to summarize, I have to mention this, a paper you can find in Science from last year shows for the first time that the age of the small chondrules that you find in meteorites are starting out at time zero, not at a few million years later, as people have thought until now because of a measurement an error in measurement. So you can find in the same body two chondrules with very different age. And therefore, you have a problem that you need to store these chondrules. You need to make them at very different times with, for example, accretion rate changing with a factor of 1,000 from here to here. You still need to be able to make the same type of melted droplets. And you need to store them. And I think that the answer to this is that you store it in the envelope by ejecting them with the outflow. This is another paper coming out of the same type of project where we show that transporting supernova ejecta from nearby supernova is sufficient to explain the early abundance of 26 aluminum in the solar system, which is another important property. Okay, so here is the main result. This resolves the issue of angular momentum transport. And rapid accretion does not require the magnetorotational instability. I think that's a dead end. It's a side path. It relies rather on the large-scale fields that the people investigating MRI have sort of not really wanted to touch for a long time. But large-scale fields are much more efficient in transporting angular momentum than MRI. Second point, magnetic braking is not catastrophic. It's the chaotic behavior of the magnetic field coming in, which is the savior. It would be catastrophic if the magnetic field was laminar. So I think the standard accretion disk scenario, the so-called SAD scenario, is outdated. We should not really only think of transport radially. That's what the standard accretion disk scenario does. It only worries about radial transport and not vertical transport, which I think is more important. So this shows that star and planet formation depends crucially on B, and therefore a pseudo-random variable that determines what kind of a solar system you get is how much magnetic flux did you happen to catch from the interstellar medium as you formed the core. This cannot be a constant. It must be something that varies with an order of magnitude, and then the energy varies with 2 orders of magnitude. So I think that could be one reason that when you look at observed exoplanetary systems, they come in very different scales. Ours is a big one, and there are many much smaller ones. And you can blame migration, but I think it's easier to explain it by in situ formation at those scales. And you can read a paper by Ed Chang from this year about a similar idea. In fact, the surviving angular momentum in this case is actually a random component, and it's not sort of a small fraction of the initial angular momentum. And the disk tumbles rather than stays in the same plane. This also illustrates the central importance of bipolar outflows, which carry 50% of the mass, perhaps, but carries even much more in angular momentum and energy, which are higher moments of motion. So these are first-of-a-kind simulation, covering in 9 orders of magnitude, and anchored in GMC scales, which is where you can really anchor things if you want to do it from scratch, ab initio. And it's a proof of concept where the plan is to get a statistically significant sample, and it really illustrates the central importance of magnetic fields in this process. Thanks for your attention.